Good morning, good afternoon, and good evening, everyone. The authors and invited guests, welcome to Technical Session 14A. I'm Sanskrit Thankar, and I will be moderating this session today. On behalf of the Global Knowledge Research Foundation and GR Scholastic, it is my pleasure to welcome you to the last day of the 11th International Congress on Information and Communication Technology. That is ICICT 2026, London, UK. I hope you find today's session engaging, informative, and insightful. In this session, we have 6 presentations. Each presenter will have 12 minutes for their presentation, followed by 3 minutes for the Q&A. I will give a gentle reminder when 2 minutes remain. I request all participants to stay connected until the closing minutes. If you have any questions or updates, please feel free to share them in the chat box. I would also like to apologize in advance for any mispronunciation of names during the session. Before we begin, I would like to introduce our session chairs. We have Dr. Bhumi Gupta, who is an associate professor at Maharaja Agrasen Institute of Technology in New Delhi. The expertise in civil engineering, computer engineering, and transportation engineering. Her specialized skills include transportation planning, disaster management, and computer communications. Dr. Gupta is dedicated to advancing research and education in these interdisciplinary fields. Welcome, Dr. Gupta. Would you like to share a few words with us? This session is also co-chaired by Professor Vangelis Malamas, who is a professor at the Hellenic Open University School of Social Sciences, Greece. His core areas of expertise include cybersecurity, emerging technologies, and academic research, with a focus on advancing secure and innovative applications of modern digital technologies within social and educational contexts. Welcome, sir. Would you please like to share a few words with us?
Yes, thank you very much. I'm honored and I want to thank the organization committee for inviting me for this session chair. I hope all the authors to make some good presentations. I already saw the abstracts of the papers and they seem very interesting, so we can get started. That's for me. Thank you.
Thank you, sir, for your encouraging words. Now let's proceed with the presentations. First up, we have Callum Ursul, who's presenting Language Recognition and Audio Text Conversion System.
Hello. Should I share my screen now?
Yes, please.
Is it visible?
Yes, it's visible.
Okay, thank you for your confirmation. So, hello everyone, my name is Ursu Kalin, and today I have the pleasure of presenting our project titled Bridging Communication Gaps. This work developed alongside my colleague Nicoleta Cristina Gaitan from Ștefan cel Mare University of Suceava, Romania, proposes a real-time system for sign language recognition and its conversion into audio and text formats. Our goal was to facilitate direct and independent communication between individuals with different sensory impairments. One second. To understand the importance of this system, we must first define the problem, the sensory barrier. Imagine a direct conversation between a deaf person who relies exclusively on sign language and a blind person who relies on auditory cues. Because they lack a shared sensory channel, direct communication is almost impossible. Currently, these interactions require the presence of a human interpreter or the use of not so real-time tactile devices such as braille systems making the conversation slow and indirect. There are already solutions on the market, such as smart gloves equipped with sensors, but these come with major limitations. Prohibitive costs. The specialized hardware is extremely expensive, which severely limits accessibility. Physical discomfort. The user must constantly wear a restricted glove with cables or contact sensors, which become uncomfortable for daily use. And finally, the lack of autonomy. When relying on human intermediaries, conversational privacy is compromised, and individuals with disability lose their independence. Our response to this limitation is a computer vision-based prototype. We created a wearable, low-cost system that reads sign language using only a video camera. Processing is done completely on device, so it does not require an internet connection. The system translates gestures into synthetic speech for blind users and simultaneously display text on a screen for people without hearing impairments or who do not know sign language. And most importantly, we completely eliminated the need to wear uncomfortable sensor-laden gloves. Our system architecture is built on three essential pillars. The camera as an input module, which continuously scans the environment and captures hand movements in real time. Processing unit. Here we used MediaPipe framework to create a 3D map of the hand with 21 key points, and the machine learning algorithm translates the spatial data into words. And finally, output module, which transforms the recognized words into voice, text-to-speech, and displays them on an energy-efficient LCD screen. At the hardware level, we focused on efficiency and compact size. We used an OV2640 camera module, chosen for its good resolution and ability to stream fluid video at around 30 frames per second, which is essential for capturing rapid hand movements. Additionally, the system is optimized to consume very little energy, averaging about 1.8 watts. With a standard 5000 milliamp battery, the device can provide approximately 6 hours of continuous use. The heart of the visual recognition system is the MediaPipe integration. To enable rapid processing on a small device, MediaPipe uses a two-stage pipeline. First, it detects only the palm. Once the palm is localized, the system ignores the rest of the background. Then, a single-shot detector analyzes the palm area and generates a precise 3D anthropometric map. This map extracts 21 key coordinates on the wrist, fingers, and knuckles, accurately capturing the trajectory and position of the hand in space. You might ask, how do we turn those 21 points into words? We use the supervised learning algorithm. The neural network analyzes the distance and angles between these points to understand finger flexion and palm orientation. For this prototype, we created a custom dictionary of 9 foundational signs to demonstrate the concept. An important innovation here is semantic segmentation. We implemented a special gesture for testing purposes, more likely, called the dot, which acts as a punctuation marker. When the user makes this gesture, the system knows the sentence has ended and triggers the audio playback of the complete phrase. No matter how good the algorithm is, if there is a delay, the conversation will not be natural. The performance of our prototype is excellent. In the prototype phase, we managed to process 28 frames per second directly on the wearable device. Furthermore, the end-to-end latency, the time from making the gesture to its recognition, is only 220 milliseconds. This speed guarantees fluid, responsive interaction, exactly how a real-life conversation should be. We tested the system with two groups of users. Experienced users who already knew our custom dictionary were able to construct sentences very fluidly and without hesitation, fully exploiting the system's 28 frames per second speed. Novice users experienced minor difficulties at first, tending to pause and check the screen to ensure the gesture was read correctly. However, their adaptation time was short, and their performance improved noticeably after just a few minutes of familiarizing themselves with the device visual feedback. We were proud of this prototype, but we were also aware of future challenges. First, the algorithmic robustness needs to be improved to better handle the noise created by transitional movements between two entirely different signs. Second, we want to expand the vocabulary beyond these 9 testing signs, integrating more complex language models to support unconstrained natural dialogue. And last but not the least, we want to transition from laboratory tests to real-world trials over a long period to analyze long-term comfort and community acceptance of the device. And in conclusion, computer vision-based technology has enormous potential to break down sensory barriers and provide independence for people with disabilities without big costs or physical discomforts. Thank you very much. If you have any questions, I am open to answer them.
Mr. Ursu, may I ask a question?
Of course.
A very interesting, idea which address a real problem. If you can go back to your last slide with the limitations, uh, could you the slide before the questions? Yeah. Here regarding the algorithmic robustness, you say your current device struggles with rapid signing transitions and intermediate movement between signs. Can you elaborate a bit more on this?
Okay, so to be able to achieve processing on device, we
Yeah.
were only classifying standing signs. Yeah. So we were not doing some temporal movements like when we researched this first, we looked into different types of sign languages. And we were discovering that many of them have moving hands gestures. Yeah. So not like uh, you put your hand on one position and it's a letter, or
Okay.
you only put your hand on one position and it's a word. Yeah, so they are dynamical.
Okay, I got the point.
Yeah,
Uh,
and
uh,
thank you.
yeah, please continue.
No, and that I was gonna say, we are working with stationary signs, not dynamical.
Okay, thank you. Well done for your work.
Thank you.
Thank you, Mr. Ashok, for your presentation. Now we have Victoria Erskine Arias presenting malicious URL detection using random forest.
Hello. I'm going to present my screen. And now can you see my screen?
Yes, it's visible.
Yes.
Okay, thank you. Good morning, good evening, and good afternoon. My name is Victoria Orozco. I am from Costa Rica, and I'm going to present malicious URL detection using random forest. My agenda for today is introduction, cybersecurity, experiment and results, and then the conclusion and future work. In the introduction, this research explores how machine learning techniques can improve the detection of malicious websites. The main objective was to evaluate whether combining multiple types of website features improves detection accuracy compared to traditional URL-only approaches. Limitations of traditional detection focus mainly on URL lexical analysis. Attackers mimic legitimate URL structures. SSL certificates can be obtained by malicious actors, and URL-only detection might not be sufficient. Then the problem is that malicious websites steal sensitive information. Attackers replicate legitimate platforms, and users often cannot distinguish fake websites. Cybersecurity. In the global context of cybersecurity, over the past decade, internet usage has expanded significantly worldwide. Digital services such as online banking, e-commerce, and cloud platforms, are now essential in daily life. However, this digital transformation has also increased the exposure to cyber threats or attacks. Phishing and domain spoofing attacks continue to grow in sophistication, and attackers replicate legitimate websites to steal sensitive information such as login credentials, personal identification data, and financial information. One of the reasons phishing remains effective is that it exploits with the human trust rather than technical vulnerabilities. So for this, the need of intelligent automated detection system. Experiment. The research question of the experiment was, does combining URL, metadata, and image analysis improve malicious website detection accuracy? The objective of the research, was design a detection system, integrate multiple feature types, use random forest algorithm, and experimentally evaluate feature combination. Why random forest? Random forest was selected because it is a robust ensemble learning method. It handles heterogeneous feature types efficiently, which was important since this study integrates structural, metadata, and visual information of the websites. Another important advantage is interpretability. Random Forest provides feature importance analysis, allowing us to understand which variables contribute most to classification problems. Additional, it is resistant to overfitting when combined with cross-validation techniques. The methodology overview of the experiment, we developed an experiment that control experimental environment. The methodology includes feature extraction, data preprocessing, model training, cross-validation, performance evaluation. To reduce the overfitting risk, a stratified training test splitting was applied to preserve class balance. Cross-validation, multiple false was also performed to evaluate model stability and generalization performance. The feature types, 3 types of features were analyzed. First, URL structural feature, such as length and domain format. Second, metadata elements, including security-related headers like HSTS and contents security policy. Third, image-based feature extracted from website content. The goal was to test whether a multimodal approach improves detection performance. The experimental design, first we extract website features, then process features in the random forest model, and then classify as malicious or benign. For the model validation, we use stratified data splitting, cross-validation, multiple iterations, and stability evaluations. And then the results of the experiment. First, the classification problem results. The classification model achieved strong performance across all evaluation metrics. Precision was about 95%, meaning that most websites classified as malicious were indeed malicious. Recall was also about 95%, indicating that the model successfully detected the majority of malicious websites in the dataset. The F1 score, which balances precision and recall, remained consistently high across iterations. This balance is very important in cybersecurity applications where both false positive and false negatives have significant consequence. In the case of false positive may block legitimate websites, reducing user trust, while false negatives may allow real threats to pass undetected. In this study, both error types remain low, indicating a strong classification capability. The confusion matrix analysis provides deeper insight into the model's behavior. True positive and true negatives were significant higher than false classifications. This indicates that the model achieved a good balance between sensitive and specificity. Then the feature importance. One of the most important findings related to feature importance was that despite evaluating a multimodal approach, URL structures features remain influential predictors. Metadata contribute to classification accuracy, and image-based features show very limited discriminate value. Here in this image, you can see the importance that the random forest classification system gave to the features. Main emphasis is placed on the URL and the site configuration. However, it can be observed that the metadata have an influence on determining the site type, like X content type option or HSTS metadata information. Then the regression experiment results. Regression-based evaluation was also conducted to assess numerical consistency. The R-squared value was approx 0.95, indicated a strong explanatory power. Error metrics such as mean squared error, root mean squared error, and mean absolute error remain low and stable. This confirms that the model predictions were not only accurate in classification terms, but also numerical consistency. Some key insight and limitations. Many websites lack security metadata. Metadata inconsistency reduced reliability. Data set focused mainly on Costa Rican websites and limited geographical diversity. For conclusion and future work, in conclusion, the random forest model achieved high detection accuracy with a strong precision, recall, and stability. URL structural features remain the domain predictors. However, metadata and other security tags are considered important when classifying websites and should be included more frequently on websites. Future work includes expanding the dataset geographically, not only in Costa Rica, testing more advanced machine learning models such as gradient boosting or deep learning, and evaluating performance in real-world deployment scenarios. And that's my presentation. Thank you.
Uh, Hi, also an interesting work. Um, I think it's an emerging topic regarding the security over the internet, so it's very interesting. I wanted to make one question regarding have you made a comparison with other relevant solutions that doesn't use a random forest or something similar, but to see how this increases the accuracy of your mechanism.
Yes, first I researched many other works, and I realized that the random forest is not very used, and I began to investigate about random forest, and I was captured because the random forest is robust, handles multiple feature types efficiently, and provide the importance of the features. And I want to know what is the importance of other things, not only for URL structure analysis. And for this, I select random forest in this case.
Okay. I would suggest in your future work to see it will help to have a comparison in order to show the benefits of your work. So thank you very much for your presentation.
Thank you.
Yeah, I have a suggestion to make, ma'am. There's a question also. Since you have worked on legitimate and illegitimate URLs, there are many attacks like phishing and all that. But when it comes to random forest and similar kind of models, I believe that when it comes to newly updated data or the newly added URLs, this particular model seems to be ineffective. I think this is a suggestion from my side to incorporate some implementation in your model when it comes to updations or newly fetched data or newly launched website data. This is my suggestion to you. You can add it as a limitation and then work on it also.
Okay, thank you very much.
Okay, thank you.
Thank you, Ms. Maria, for sharing your work and to the shares for that matter. Now we have Bianca Batinas presenting Reducing Operator Cognitive Load in SAR, a proactive reasoning role with an LLM-driven agentic code. Ms. Bianca, you may start your presentation.
Thank you, listener. Now, can you see the presentation? 1 second. Can you see the presentation?
Yes. Your presentation is visible. You may start.
Nash Bianca. I'm a student from Stefan cel Mare University of Suceava. And today I want to talk about a major problem in search and rescue, how to handle information. Our project focuses on reducing the cognitive load for drone operators using LLMS systems. Now, we all know drones are great for disaster, but there is the issues. During a mission, there is too much noises or activity. An operator has to fly the drone, watch the screen, and make decisions. This leads to human errors. We want to prevent these errors, and we propose the cognitive agentic architectures to transform the drone to a passive drone to a partner. we have built a system that combines perception, reasoning, and action. For the perception part, we have the sensor and the custom YOLO 11 for detection. For the reasoning part, we have the agentic core, and for action, we have the payload delivery. To test this system, we built our own drone using a modular frame. We have a battery that help us fly the drone for around 50 minutes, maximum 50 minutes, and we can carry up to 1 kilogram. On the drone, we have one camera, one lidar to see the distance from the ground, and one GPS to locate the drone and the people in the video stream. For the system, we are using a custom YOLO model because it's fast for real-time detection. We customize the model to detect people and their states. It can tell if a person is walking, is sitting, or if they are under debris. For this part, we made a small trade-off. This means we made the model to always detect the person, even if we don't know the postures. But we never miss the human presence. After the person is detected in the video stream, the data is sent to agentic core. Perception agent takes the data from the drone, and at the same time, the perception agent sends this data to the database. That means the memory agent and the reasoning agent, risk evaluation agent, recommendation. This is the feedback loop. After these three agents see the context and the data received, these three reports are sent to the orchestrator agent. These orchestrators generate a final report on the recommendation. This feedback loop is the most important in the agentic core because we prevent the propagation of illogical data. Because the AI can make mistakes, we can force the AI to reevaluate the data sent to the orchestrator agent. This step adds a few seconds of delay, but it makes the system safer. Once the agentic core confirms the situation, the drone operator can send a physical response. We design a 3D printed structure with a servo control mechanism. We can see it in the photo. This allows the drone to carry and release a rescue kit to the victim or a radio or something else. In conclusions, our goal to create a bridge between the drone and the human, or symbiosis between them. Thank you for attention.
Yes, ma'am, it was good work. I think that you have initiated good model into it. And all the best because I think this is a new area which you are working in. And research and architecture has been all done very nicely. All the best for this. Thank you.
Thank you.
Ma'am, can we move to the next paper?
Yes.
Sanskriti, ma'am?
Hello. Yes. Sorry, there was an internet. Yes, we are going on with the next paper. Now we have Leonardo Douglas presenting safety monitoring technologies for creating hazard zones around heavy equipment in construction and mining environments, a systematic review.
Hello, everyone. Everyone can see my screen. Hello.
Yes, we can see your screen.
Oh, thank you. So, good afternoon. I am Leonardo Dolch, and I'm going to present our work on the systematic review on safety monitoring technologies for creating hazard zones around heavy equipment in construction and mining environments. So this work was developed at Cyber Physical Systems Laboratory and Research Group at PUC-PR, in collaboration with Alisson Mafra, Luiz Toledo, and professors Marcelo Pérez and Marco Teixeira. So the scenario is in Brazil, we had in the 2012 and 2025 1,240 excavator-related accidents. This shows the interaction between workers and heavy equipment in a dynamic construction and mine environment is a most safety challenge. This search was guided by these three questions. Which sensor configuration and placements are employed for risk zone monitoring? What detection tasks and operation scenarios these systems target? And which collision prevention strategies and triggering systems mechanics are implemented? So to structure our search, we use the PICO method, focus on excavators, heavy equipment in civil construction and mining industries, using of LiDAR, computer vision, and sensor vision, creating a safety zone and a collision avoidance on the heavy equipment. And our initial search returned at 157 records after applying the inclusion and exclusion, like exclusion is articles on PPA detection, routing planning, and matching part estimation only, and inclusion was articles from 2020 onward using sensor-based or vision-based technologies for monitoring. We end up with 42 studies in case we carry out to analysis. So these technologies we can separate in three categories. Sensor-based is only sensors like LiDAR, GPS, EMU, radar, or vision-based because uses cameras and algorithms to detection like YOLO or CNN or CNN. And there was fusion methods. We can fuse the sensor-based with the vision-based working together. As we can see here, the camera has dominance on every other technology, with followed by EMU and LiDAR. And the radar is one that has no appliances, and we can see that the camera is easily to implement. It's a low-cost way to creating these safety zones around the heavy equipment. Here is the triggering methods that they're using. The most of it is the vision plus sound signals with 40%. And we have autonomous stop, like the emergency stop, when just 22% of the appliances using. Here we had the same triggering the alert, but separate by technology. This is from the visual-based technology method. As you can see, most of it use visual signs, and almost none of that use the autonomous stop, with just a 5%. Here's for the sensor based. Here, as you can see, there is a little more appliances that use the autonomous stops with 33%. And the most of it is visuals plus sound signals with 47%. And this is for fusion method. We can see here is applies more autonomous stop with 33%. It just measured to the sound plus visual signal with 5-6%. Here is the modern and classic approaches. Its modern approaches is using the technology and some machine learning or IA to improve the performance, or the classics, because using a classic mathematics like just a difference distance the object for the matchner, or a classics algorithms. You can see the most of it uses the modern approach, and classic and modern approaches kind of equal. So here is what the appliances detect the targets. Every study will detect workers. A few separate workers from visitors. We can see a lot of the studies, the cars, trucks, every study, and rebels and static signature is the most is less. It has less works that target these objects around the heavy equipment. So as you can see, radar is a technology that there's no recent studies on it. A fact that is robust in dust environments or raining environments. And sensor fusion, it can be improved to detection reliability where the camera lacks loose effectiveness with the variation of light in the environment. So the LiDAR don't have that problem. And emergency stop with just 22% of works so reduce the dependence operator reaction time if you apply the autonomous stop on the equipment. To conclude, the vision-based method dominant but sensitive to light and dust, while LiDAR has the geometric and still degrades in dust. Or has the precision geometric and still degrades in dust. The LiDAR had a lack of the semantic understanding like a YOLO could provide. Sensor fusion improves robustness, but dust remains a challenge. Riders and explored technology for this was its resistance to particles. And for the future works with predictive algorithms like LSTM or TTC, and employ the intelligence braking to reduce the operation reaction time and prevention collisions. So thank you for your time, and I open for any questions that you may have.
I have a question. When you were talking about the workers, the environment, the vehicles, and all the things, I think you should also have included the time when the vulnerability is there, when you are trying to, monitor the data. For example, it's a daytime and it's evening time, it's night time, when the activity is there, when it is evacuation modeling or route map planning is required. All those factors should also be incorporated because the models which you have used, sensors and computer vision, they need to incorporate other variables like these also. Environmental factors and the duration and the time slot of the day when this thing is required, when the actions are required. I think that is lacking in the literature, or maybe some more papers are required to be studied for that. This is my suggestion also for you.
Yes, I don't see that for these studies. It's a very important thing. Thank you.
A small comment. Very nice. Your work. It will be useful. I haven't read the full paper. It seems interesting. Um, but given the identified gap in radar users and predictive algorithms, such as LSTM and time to collision, it will be useful if, from your research, you could give an insight on how could integrating this technology can improve proactive collision avoidance and autonomous emergency response systems, how this could evolve these systems. It will be useful as an outcome of your research, of your review. I say I haven't read the full paper, so maybe you have included, but it will be quite useful. Thank you.
Okay. Thank you.
Thank you, Mr. Leonardo, for your presentation and for your feedback. Now we have Kristen Castillo-Olea presenting use of serious games with biofeedback for interactive neuromuscular rehabilitation in older adults with cognitive impairment in rural areas of Veracruz. Do we have Ms. Kristen Olea with us here? We will be moving forward with the next presentation, which is by Lemon Vesitimov. Sorry if I mispronounced it. Who will be presenting video fingerprinting and deepfake detection for increased social network security.
Greetings, everyone. I will share now. Can you see my screen?
Yes, it's visible.
Greetings, everyone. Today, I'm gonna present our science paper titled Video Fingerprinting and Deepfake Detection for Increased Social Network Security. And the agenda for today is this, with me starting with the nature of our problem. We all know that deepfakes play a really crucial role in the ecosystem of the social networks. They are really easily created today. A normal user can go in an LLM such as OpenAI's ChatGPT or X's Grok and create deepfakes, and that could lead to a plethora of problems. One of them being impersonation. People can use the likeliness of infamous individuals in order to promote different products or in order to create blackmail material for them. Another problem with that is the spread of misinformation. Like I already said, we can use famous people in order to deepfake them and make them say whatever we want. So that is a really big problem in social networks today. But what's even more frightening is that a completely ordinary person can fall victim to this as well, because just one single image is needed to create a deepfake, not only image, but a video as well. Our proposed solution is based on this methodology. As you can see on the graph, we have two partitions. One is frame processing, where we take the input data, we split it into frames. We go over each frame and we detect whether a face is present on it. And if it is, we run it through a deepfake detection process. If not, we go straight to vectorizing the frames. We will talk more in depth about that in just a little bit. And the second partition is matching and output, where we search for matches of the given input and determine whether they exist in our database or not. And we set statuses based on the metadata for the input that we have. Our first more complex process is the face localization. Here we were split between going with feature-based localization, which proves to be simpler to implement, a lot faster in real scenarios, but the major downside with this is that it's less accurate than the image-based face localization, which is, like I already said, more accurate, but it tends to be more complex to implement and a lot slower in a real situation. In the end, we went with Cascade Heart-like features, which proved to be a perfect compromise between quality and speed, and it works for our needs. The next more complex element of our system is the deepfake detection process. Here we had three main columns that we wanted to step upon and build our system. The main one being reusability, because such function can be used not only in this system, but in other systems, which meant that we needed to make it easy to integrate. And that ultimately led us to make it accessible not only for us, but for other people. And the result was a library for deepfake recognition. This library is available for Python users, and it's a module that is trained that uses a ResNet neural network that is trained to detect deepfakes. The driver behind our decision is that ResNet is trained on the ImageNet dataset, and it's really straightforward to train it on datasets of interest. So it proved to be a good solution to our needs. The next most complex part of our system is the fingerprinting process. In related works, you can see that fingerprinting is based mostly on pixel characteristics, whereas our solution proposes a process which is based on the content of the image itself. We employ a ResNet neural network model here as well, with the caveat being that we removed the fully connected layer, thus making the model more so a feature extractor. And we get those features, we transform them, and we store them in a vectorized storage. As for the status assignment, we have two types of statuses. One is based on whether a deepfake has been detected in the image, in the input data, sorry. And the other is based on the copyright metadata that we have for the input data, which could be whether the input data is copyrighted, if it's free to use, or it can be used with a reference. This is in order to accommodate for real system usage. I'll briefly go over the implementation of this system. It's based on a microservice architecture with two modules communicating with the appropriate databases, with the client facing one using SQL database or a SQL database, and the neural network module works with a vector database due to the capabilities that such databases have in order to find similarities. Here we point out the exact technologies used, with the client-facing backend being based on the Java, the neural network module being based on Python, the message broker of choice is Kafka, and the SQL database is Postgres, and the vector database is Pinecone. Now, a bit more about the results. First, I'll start with the similarity search, which is the foundation of our copyright part of the system. As you can see on the left, we have the original data, and on the right, we have obscured data, which can be either with less highlighting, or it could be with different contrast. The system proves to deal with these kinds of changes relatively fine. As we can see, the similarity that we find is around 97.5%, with the differences between each frames being, they're under 1%. Of course, our system isn't perfect. As you can see here, on the left, we still have the original data. On the right, we have our embedded data, which basically means having one video above another with its opacity slightly decreased. In such cases, our system struggles. As we can see, the similarity percentage fluctuates between 70 and 75%, and the differences between different frames are a lot higher. In places, it jumps by 5%. It's hard to demonstrate the deepfake results without showing video, but I've selected several frames from deepfake videos that we've used, and the system appropriately classifies as deepfakes. Now on to the future work. The first part of our future work will resolve around adding an additional audio deepfake detection module, which will run in parallel with the visual deepfake detection module in order to create a more full package and a more robust solution, because as we've all seen, deepfakes are not only graphical, but sometimes people fabricate the voice of different other people. So this is one branch of our future work. The other branch of our future works is a higher level of parallelization, because right now the main problem with our system is how fast it processes input data. And I will use this as a segue to my conclusion. Currently, our system is proficient at finding similarities, and it is sufficient at finding deepfakes. Its only downsides are the need for computational power, because it's solely reliant on neural networks, and the time it takes for processing each input, again, due to the use of neural networks. And this is everything from my side. Thank you for your attention, and I'm open to questions.
Yeah, it was very good presentation. Actually, I'm more curious about what kind of image data sets have you picked up? What sort of what was the way of classifying and choosing the kinds of images or the data set you have worked on?
The datasets that we used were provided from Hugging Face. There are several deepfake datasets there. One of the main problems we found while working on this was it's extremely hard to find large datasets of deepfake images, because some of them are not available to the public, and it's not morally correct to create deepfakes. So it's hard to generate such data or to find it available online. So yeah, we relied heavily on the existing data sets that were available on Hugging Face.
Okay, thank you.
Thank you. So
Yeah, I had the same question about the datasets, but you answered it already. Great work. We expect to see the future extensions.
thank you.
Thank you, Mr. Corman, for your presentation. And with that, we have concluded all presentations for today. I sincerely thank all of our authors for the excellent presentations and valuable contributions to the session. I also extend my gratitude to all participants for being a part of this international conference. I hope this session was informative and insightful. On behalf of the ICICT team, thank you for your continued support during the 11th edition of ICICT, as well as the previous editions. We look forward to welcoming you again for the 12th edition in 2027. All presenters will receive their digital certificates via email within 2 working days. The publication is expected to be available within 7 to 8 months. We kindly request your cooperation with the ICICT 2026 team during this process. I would also like to thank our session chairs for effectively chairing the session. We now present a token of appreciation on behalf of Team ICICT 2026, the Global Knowledge Research Foundation, and our partners. Sir and ma'am, would you please like to share a few words?
Ms. Gupta, do you want to start?
Yes.
Should I start? Okay, I'll start. I want to thank all the presenters for their work. It was indeed a very interesting session, and we will, of course, wait for the published papers, which will have the full detail of what was presented today. I want to say to everyone, keep up the good work. And thanks again for the opportunity to this session to be chairing this session. Thank you.
Thank you, sir, for your kind words.
I would like to thank ICICT 26 because I've seen that this series of conference have been picking up papers across the globe from young students of engineering undergrad to PhD doctorate, postdoctorate students also. And the conference, they are doing good work. They are trying to incorporate many more themes. Themes and tracks are good. And even in today's presentations, I've seen that students and the scholars have done their best. They have tried to incorporate models, results, they have done the analysis, limitation and scope, everything is covered. I wish all the best to all scholars and students, and my best wishes and thanks to the team. Thank you so much.
Thank you, ma'am, for your encouraging words. May I please request everyone to turn on their camera so that we can have a good snapshot of the session. Thank you, everyone, for joining us today. I hope you all have a great day.
Thank you, Sanskriti. Thank you so much.
Thank you. Bye-bye.
Bye.
Bye-bye.
Thank you. Thank you.
Thank you. Bye.